All right, before we actually move on and consider the Galilean transformation, whatever that happens to be, we'll get to that in the next video clip. I wanted to take the opportunity to actually say a few more words on world lines and look at two specific examples that are going to be important for us later on in terms of trying to understand a couple of the paradoxes that arise in the theory of special relativity. And one of the paradoxes is the so-called pole in the barn paradox, and another, perhaps the most famous paradox, is called the twin paradox. And so a couple diagrams we're going to look at here. We'll see variations of them later on when we're considering these paradoxes. So I want to take the opportunity now just to introduce the ideas. So again, let's imagine a situation. We've got Bob in his spaceship traveling on at velocity v here. Here's Alice. Okay, so Alice is doing the measuring. This is her lattice of clocks, her measuring stick, as it were. We've just chosen different units here, minus 10, 0, 10, 20, 30, 40, on her measuring lattice there. So here comes Bob along, and if we imagine that, you know, at time t equals 0, he's here. So Alice records his position on her clocks. The front of his ship is at 10. He actually, his cockpit is positioned at 0, and the back of his ship is positioned at negative 10. Maybe a second later, he's moved ahead, so now his front of his ship is at 20. He'd be at 10, the cockpit, and then the back of the ship would be at 0, and so on and so forth. He'd move, then 10 to 30, and 20 to 40, and so on and so forth like that. So that's the idea. In other words, before, when we were looking at these situations, we were just imagining Bob was a point, his ship was a point, and so we'd plot that. Now let's actually plot it as an extended object here. And so this is the physical situation. This is what Alice would actually see. This is what Bob would see as he's traveling around. Now let's add the space-time diagram. So we'll use the x-axis here for Alice, and we'll add her time axis on there. And what would Bob's ship look like, this extended object? What would that look like on her space-time diagram? Well, clearly we'll use our red again. At the beginning, if we were to plot just Bob in his cockpit at time t equals 0, it's right there. Then we'll imagine that, let's put some time marks here, the tick marks for time. So at the next time, we'll imagine that the ship has moved over 10, so now he's at position 10, and so he'd be right there. And then move again, he'd be at position 20, and so on and so forth. So he would look something like that. And so his world line of Bob in the cockpit would look like that. What about the front of the ship? Let's do the front of the ship here. So at time t equals 0, it's at 10. So it would be there. And then at the next time, it'd be at 20. So it'd be here. And then 30 and 40 and so on and so forth at each time. So it's 30. And so the front of the ship, its world line looks like that. So this is the cockpit where Bob is sitting. This is the front of the ship, the world line of the front of the ship, and the back of the ship is similar. Of course, it starts off at t equals 0 here. Then as the ship moves over, 1 second or whatever the unit of time is later, it's going to be here, and then it's going to be here, and so on and so forth. And we get that as well, more or less. So this is the back of the ship. So in terms of the ship's world line, it's sort of a world, I don't know if you would call it a line, but a blob there. So it moves like this. Okay, so at any given instant, if this represents the ship, we'll do it like this. So there's the ship. Then Alice sees it here and here and here. Actually, of course, physically, she's seeing it here and then here and then here and then here and so on and so forth. She's representing that on the space-time diagram as moving along this way. So the world line of the front of the ship, world line of the cockpit, world line of the back. And so things that move in parallel, we see these are diagonal lines, of course, but they're all parallel to each other, represent a moving object, an extended object in Alice's frame of reference on her space-time diagram. Okay? And like I said, this will be important actually when we consider the so-called pole in the barn paradox in special relativity. So that's one example I wanted to do. You might, as a little exercise here, you might think about what if Bob was moving backwards? What would that look like? If he's moving in this direction, what would the world lines be like? So I'll leave that as a little thought exercise for you. Now let's consider a second one. We'll just leave this up here. Let's do a second example of some world lines here. Oh, actually, by the way, before we get there, also let's just do a quick sketch of what are Bob's world lines for his ship in his frame of reference. Okay, again, just to maybe reiterate the point here. So minus 10, 0, 10, 20, and this is x Bob and t Bob in his frame of reference. Of course, in his frame of reference, he's stationary. The ship is stationary. It's not moving as far as he's concerned. He always stays at position 0. So his world line, as we mentioned in the previous video clip, if something is stationary in a frame of reference, the world line is just vertical. So he's just staying here in the cockpit. At any given time, whatever time t we're talking about, he is at 0. And the front of the ship stays at, get this right here, stays at 10. And the back of the ship stays at, not 10, but minus 10 here. So the back of the ship is here. So on and so forth. So here's the front of the ship world line. Here's Bob's world line in the cockpit. And here is the world line of the back of the ship. So as far as he's concerned, the world path, as it were, of his ship, the space-time path, the path in the space-time diagram, not the actual physical path. The physical path, he's just moving along. Well, he's stationary. To Alice, he's moving along like this, is just straight up and down like that. Okay, so that's that example. Let's look at a different one here. We'll just call this, in general, x and t. So it's going to be some observer. It could be Alice, could be Bob, could be any observer in their frame of reference, meaning they're stationary. They've got their lattice of clocks they're measuring things with. And they analyze the motion of an object, and they get something that looks like this on their space-time diagram. It moves out to here, and then over to here. That's the space-time diagram. Here's a question for you. What does this represent in terms of the physical motion of an object? Okay? If you want, you can pause the video for a minute here, ponder that, figure out, okay, what's actually going on? Remember, this is for the x-axis, motion along the x-axis. We have our space-time diagram that represents the time, position and time of a given event. But what's going on if we were to translate this back into the physical situation of motion along the x-axis? What does this represent? So again, if you really want, pause it or ponder a few minutes on that. Let's think about this then. Okay, so what this is saying, we're starting at t equals 0 here. And it's moving out this way, straight line. So it's going to be constant velocity, motion. And so time is going on here, time 0, 1, 2, 3, 4. So what this is telling us up to that point, it's moving in the positive x direction through time. So up to this point here, it's moved out maybe, put some things there. We'll say 1, 2, 3, something like that. So it's at position 3 at some given time. Okay, so we'll go 1, 2, 3, 4, 5, 6, 7, 8. Okay, so at time t equals 4 seconds, 4 minutes, 4 years, whatever it happens to be, it's at position 3. It's moved in the positive x direction. And if it kept going, it just keep moving in the positive x direction. But evidently, it stops and changes direction at that point. And now, at time t equals 5, it's back. So here's the t equals 5 point right there. It's back someplace in here. Sorry, my diagram's all messed up there. And then at t equals 6, it's here. At t equals 7, it's here. It's moving back this direction. It's moving to the left on the x-axis. And at t equals 8, where is it? It's back where it started from. So a world line that looks like this, where it moves out like that and then back like this, represents an object that has moved out to position 3 or wherever it is, and then has moved back to position 0 again. Out to position 3, then as time continues going on, it moves back to position, not position 8, that's time t equals 8, but position 0 where it started from here. You could also have something like this, a world line like this, where it moves out here, moves back there. So this time, starting at 0, started at position 5 or 6 out here, moved out to some further position, and then moved back there. So again, along the x-axis, it's moving out, and then back again, moving out and back in. Or if you want to go the other direction, you can move this way, and then to some position like that. So there it's moving to the left, and then back to the right again. So it's helpful to sort of think about these things, get a more intuitive understanding by able to look at a space-time diagram and understand what's actually going on, what does it represent in terms of the motion going on. And as I mentioned, this example here we did will be useful when we consider the pole in the barn paradox. This example will be very useful when we consider the twin paradox later on. So that's a few more words on world lines, and then in the next video clip we'll talk about the so-called Galilean transformation.